Hi, this is Vinay, and in this ICP we are going to perform the text generation by using any of the data, choosing of the data on our own, and then we need to make the 4 changes that were explained in the class, and we need to give a logical explanation for the changes that we have done in our source code. So the requirements of the ICP first step is the successful executing the code and making the 4 changes in the model, then using a new and good data set, then providing the logical explanation for the changes that we have done. So now let's move on to our code. So here the first step here is importing the required libraries. So here we can see that we are using the 4 libraries. The first one is a TensorFlow, next one is a NumPy, next OS, next the time. So basically NumPy is used for performing the numerical operations for the arrays. Next importing the OS, that's the operating system. Next importing the time for the time related functions. These are all the 4 libraries that we are importing. Next we are uploading the file. So for this I am choosing the file. Here we are using the file ICP5 text1. Here basically the file we are choosing, or the data that we are using here, is extracted from a famous novel, Rich Dad and Poor Dad. So we have taken a part of the text, which is around 45,000 of characters, and we have converted it to the .txt format, and we are uploading the same file into this. So here we can see that this is the file name and this is the text. I had 2 fathers. This is the start of the text. So after this, here we can see that next we need to open the text and we need to convert it into a list. So for that we are using the open function to open the text, and we are reading it as a para. Then by using the read lines we are converting it to a list. So here once we run this one, we can see that the data here, this is the data, and next I'm displaying the length. It's basically the paragraphs in the text. So here it's around 36 paragraphs. Next we are displaying the count of the characters. So here for that I'm first using the temporary variable. I'm storing it as a string, declaring just a temporary variable. Next I'm running a loop for I. Next I'm running a loop j for the range of 0, len of I, so that each and every character is moved into the temp. And next I'm finding the length of the string. So for this, here I can see that the length of temp or the string or the total number of characters is 45,130. Next the step is to find the unique characters. So here in order to find this, we are going by using the sorted function, and the sorted function basically returns the sorted list of the specified iterable object. Next, by using the set function, we are creating a set object that's a kind of set with all the unique characters. We are printing this set, and next here we are printing the length of the unique character. So we can see that we have 74 unique characters. So after this, the main step or the crucial step here is that we need to map all the unique characters that we found to the indexes, so that it is useful during the vectorization, so that the model gets easier to be predicted. So for this we are creating 2 lookup tables. First lookup table, here we are assigning the changing the characters to numbers, and second one we are mapping the numbers to characters. So in order to map the character to numbers, we are using the enumerate function. So enumerate function basically assigns the index to each and every element in the list. So here we are saving those in a variable character to index, and for the second mapping, that is numbers to characters, we are using the index to character, and this is achieved by using the np.array. And next we are displaying the mapped variables. So here we can see character to index. We can see that for the 74 characters the indexes are assigned. Next we are printing the index to characters. This is the indexed character. Next step is we are assigning whatever the text we have stored in the temporary. We are basically assigning the indexes to it. So first letter of our text is I. So for in the unique character we can see that for I it's 25. So when I try to print the text as int, it says that first word is 25. So in this way, we are assigning the text as integers, and we are storing in this variable. We can run this and see. Next, we are giving a sequence length. That means the maximum amount of characters that can be stored in a sequence. So the sequence length we are taking here as 50 and examples per epoch. So that is the length of temp. That's 45 130 by 50, and we are printing the value. It's 884. Next, we are creating training examples or targets. So basically, in this step, we are trying to convert the text vector into a stream of character indices. This is achieved by this tf.data.datasets from tensor slices, and the variable is text as int. Next, whatever the data that we got in character dataset, now I'm trying to predict the data by using character. So here for I in character dataset, take 9. So I'm taking the 9 characters, starting 9 characters, and I'm trying to print the data. Here I can see that when I try to print the data, it's of I had 2. So this count is 9. Next step is the sequencing of data using batch function. So batch function basically creates a group of characters based upon the given sequence length. It's created kind of batches. So for that, here we can see we are storing the data in the sequences for the character dataset by using the batch function and sequence length, and we are using the drop remainder equal to true. And next, we are just trying to print the sequences that we are using. So here I am printing the 9 sequences. So each sequence has 50 characters. So 9. Next step is to transform the data. So basically here we are using the map function to transfer the data. Basically in this step we are one second, I think this is not now here we are defining a split input target with a variable chunk. So basically here we are using 2 variables, input text and target text. So input text will take the 49 characters because we are defining it as a -1, so it will ignore the 50th character. And target text, it will start from 1, it will not start from 0. So that's the target text. So we are quoting an example for this. So here example to display the input and target data. So we are taking the first sequence and we are printing the input data and the target data. So basically here we can see that this is I had 2 photos and this is up to 49 character, not up to 50th. And the target data is also from the index 1. So I is missing here. So this is the input data, this is the target. Next, shuffling of the data. Before training the data, we need to shuffle the data and we need to pack them into the batches. So here we are using the 2 functions, shuffle and the batches. So we are declaring the variables batch size. So here we are choosing the batch size 128 because we need to get the less loss. And so the batch size is 128 and the buffer size is 1000. Buffer size is nothing but to hold the data until it's getting used. So it can store up to 10,000 of characters in this buffer size. Then we are using the dataset variable, and in this we are shuffling the data and we are packing it to the batches. So once we run this and we are displaying the dataset. So this is the dataset. So here we can see that element specification, tensor spec is shape is 128, 128, 50. Data type is int 64 and tensor spec. Next, we are defining few parameters for building the layers. So here we are using the vocab size equal to len of vocab, that is 74, and embedding dimension we are giving it as a 256, and RNN units we are giving it as a 1024. Next step, we are building the model. Here for building the model we are choosing the sequential model, sorry. Then we are adding the layers to it. So first layer is embedding. So for that we are giving the parameters as vocab size, embedding dimension, batch input. Where batch size is 128, none. And next layer is the LSTM layer. We are choosing the LSTM is one of the change that we are performing in this code. The LSTM is the long short-term memory. So basically here we are using this LSTM first to overcome the vanishing gradient issue, and next we know that we are using around a long text so that it should always remember the previous memory or the hidden state. To overcome the issue, we are using this LSTM layer. Since the text is long, we are adding the LSTM layer with the parameters as a RNN units and return sequence. We are giving it as true, stateful is true, and recurrent initializer we are going for blowout uniform. So here we are building the model, and we are adding another layer as GRU and another one as a depth, and we are returning the model. So here we are building the model. We can see that the model is built. Next we are just displaying the batch prediction. So what exactly we are using the batch prediction here is that here we are printing the next we are displaying the batch predictions. Here on this one we can see that batch size it's a 128, sequence length is 50, and vocabulary size will be 74. Next we are displaying the model. Next we are going for the, here we can see that while displaying the model, we can see these are all the layers: embedding layer, LSTM layer, GRU layer, dense layer, and total number of parameters are 11,63,370, and trainable model and non-trainable. Next step is here we need to do the actual prediction from the model. We need to sample from the output distribution, and we need to get the actual character indices, and the distribution is defined by the logistic character vocabulary. I think let me run it from the start. There is some issue. So we can see that we are printing the example batch predictions. We can see the batch size as 128, sequence length as 50, and the vocabulary size as 74. And next we are displaying the model. Oh no, it will get executed. So here we are doing the predictions. So this is the highs. Next, we are defining the loss function. Basically, here we are defining a function with the parameters as labels and logist, and the loss function we are using here is a sparse categorical cross entropy, and then we are trying to just predict the shape, and we are printing the scalar loss. So here we can see the prediction step: 128 as a batch size, 50 as a sequence length, and 74 as a vocabulary size, along with the scalar loss as 4.3. Next, we are training the model. Here we are using the optimizer as the Adam. We know that Adam optimizer is best because of its features, and it always works good with the default parameters itself. So we are choosing the optimizer as Adam and the loss as the sparse categorical cross entropy. After that, we are creating the checkpoints to ensure that the checkpoints are saved during the training of data. So here, by using the tf.keras.callback model checkpoint, we are saving all the data. Next, the key step where we need to evaluate the model that we have built. So for that, we are using the data set, and epochs we are giving it as 20, and the callbacks is a checkpoint callback. So here the reason why we are choosing epochs 20 is that when we have used the epochs, then we can see that there was a lot of loss in the data. So for the epoch equal to 20, there was a less loss compared to the epoch 10. So this is one of the things that we have done in this, and let's see. So here we can see this is running for the 20 epochs. You see that the loss gradually starts decreasing in each epoch. Overall, it takes around 2 minutes for this epoch for this model to be evaluated. It took around 48 seconds. Next step here, we are restoring the latest checkpoint to keep the prediction step simple, and hence we are using the batches as 1. Because of the way RNN state is passed from the time to time step, the model of only accepts with a fixed batch size 1 build. So here we can see that here we are building the layer once again with the embedding layer, LSTM layer, GRU and dense, and here the batch size for each and everything is 1, and these are the shapes, and these are the total number of trainable parameters, non-trainable parameters. And the next step is the key step. We are going to predict the model, or we call it as a text generation. So here basically we are creating a definition which is generate text with the parameters as model or the starting length. The sequence of steps here is that first step, we are building a function which predicts the text by flowing through a sequence of steps. Now we are going through the steps. So first step is choosing the start string and then initializing the RNA state and setting the number of characters to generate. So here I'm using the number generator as 500 characters. Next step, then the prediction distribution of the next character using the start string and the RNN state. So here we are converting our start string to the numbers. That means the vectorization, and we are storing it in the input eval variable. Next step, here we will be using the categorical distribution to calculate the index of the predicted character. Then we will use the predicted character as a input to the next model. Then we will run the return by the RNN state return by the model is fed into the model so that it has now more context instead of only one character. So in this way, the text get added and concatenated. So here we are setting the temperature. One of the changes that we have made in the source code here is that we are using the temperature as 0.5. Lower the temperature is the highest the predicted or the accuracy. So if we put the temperature as 10, the prediction or the accuracy of the data is less, and there will be more mistakes. So to overcome that issue, we need to set the temperature to the lowest. So here I am using the temperature as 0.5. And the last step and the final step, here we are passing a start string as the managers, and we are asking the model to generate the text or to predict the next text. So once we run this, this is the output. This is the prediction or the text generation. And this is the final output. Thank you.